thanks for the introduction, and thanks for having me here. So in this talk, we're going to analyze a set of Bayesian nonparametric time series models that are useful in describing a large class of complex dynamical phenomenon. So can you hear me in the back? I heard. No, you can't. Right. No, I know. But so, yes, in the back or no? Kind of. Okay. Well, I'll speak up. So this is joint work with Eric Sudderth at Brown, Mike Jordan at Berkeley, and Alan Wilsky at MIT. So one classical approach to time series modeling is that of the autoregressive process, which assumes that each observation can be modeled as some linear combination of the previous R observations plus some additive Gaussian noise. Well, a slightly more descriptive formulation is that of linear state space models that assume that there's some underlying state, X, that yield the past and the future of this process conditionally independent. So in this formulation, the state is assumed to evolve according to some fixed dynamic matrix A plus some additive Gaussian noise. And here, this noise can account for things such as inaccuracies in the dynamic model or external perturbances to the system. And then the observations are assumed to be some linear projection of the state also corrupted by additive Gaussian noise. And so these models are often referred to also as dynamic linear models in statistics or linear dynamic systems in the control literature, and they can be equated with autoregressive moving average processes. Okay, well, a much more general formulation is that of nonlinear state space models, which assume that both the state evolution and the measurement mechanism can be nonlinear, and that the noise processes can be non-Gaussian. And although oh, sorry, I guess we're getting slightly cut off here. But although potentially a very descriptive formulation for time series, this general formulation tends to lead to a lot of issues in terms of computational tractability. And so as such, a lot of work has really focused in on this region, which represents a trade-off between the expressivity of the model and computational tractability. So we're also going to hone in on this region, but within a Bayesian nonparametric framework that allows for data-driven flexibility in the complexity of the model while maintaining a number of nice computationally attractive properties. Okay, so there's a large class of data sets that can be categorized as exhibiting very complex but patterned behaviors. So, for example, considering the following data sets, and you might be sitting there wondering, what do these have to do with each other? How does the problem of segmenting conference audio into a set of speaker labels relate to analyzing the dance of honeybees? And what does that have to do with describing human motion, no less trends in stock data? Well, the complex dynamics present in these data sets can be described using what are called Markov switching processes. So, for example, honeybees, which appear to have rather chaotic motion, can actually be described as switches, Markov switches between a set of dances, each of which can be described using simple linear dynamical models. Okay, well, previous approaches to analyzing these data sets, such as the ones presented in these papers, relied on a lot of application-specific information in order to fix the number of dynamic modes, or relied on heuristics in order to infer it from the data. So again, instead, we're going to cast the problem within a Bayesian nonparametric framework and show how the Dirichlet process provides a useful prior. Well, the clustering properties induced by the Dirichlet process have been exploited in many standard mixture modeling applications. So just as a toy example, imagine that you have some data shown here that you want to model as a mixture of Gaussians with an unknown number of mixture components, which in this case happen to be 3. Well, the Dirichlet process allows you to infer this from the data while still allowing for new components to be added to the model as more data are observed. Okay, but instead of this type of static data scenario, we're interested in time series, specifically modeled using Markov switching processes such as the classic hidden Markov model. And here, our goal is to cluster the observations based on the underlying dynamics. Okay, and so by employing Dirichlet processes in this setting, it allows for uncertainty in the number of dynamic modes. Well, up to this point, I've assumed that we have a single time series for which we want to define a flexible model to describe the dynamics present in that time series. Well, an open question is, how does one model multiple related time series? So, for example, imagine you have a collection of videos of people performing some set of exercise routines. How do you transfer knowledge between these different time series? So, by jointly modeling the time series, you can both improve parameter estimates in the face of limited data, in addition to just finding interesting structure and how they relate to one another. So in the second half of the talk, I'm going to describe how an alternative Bayesian nonparametric approach, specifically based on the beta process, allows us to start addressing these questions here. Okay, well, before we get to modeling these types of time series, let's look at a single time series with these types of pattern behaviors. Okay, well, one classical approach is that of the hidden Markov model. And specifically, the hidden Markov model assumes that there's some discrete valued latent mode sequence, which is modeled as Markov with respect to some collection of transition distributions, pi k. So in the motion capture example, sorry, everything seems to be cut off on the side, but in the motion capture example, these underlying mode sequence might represent a set of action labels such as jumping jacks, squats, and so on. Well, the HMM assumes then that conditioned on this latent mode sequence, the observations are independent emissions from some family of distributions, which in this case we're taking to be Gaussian. So for example, maybe our observation at time t represents a vector of body position measurements at that time point. Okay, well, one can view a sample path of the mode sequence as a walk through the following mode versus time lattice. So let's imagine that at the first time step we start in this second dynamic mode, which might represent jumping jacks, and we have the following set of possible transitions where the relative weights of these arrows captures the probability of taking each of those transitions. And that's captured by that mode's transition distribution, pi 2. Okay, so then imagine at the next time step we persist in the same jumping jack mode, and thus at the next time step we have the same set of possible transitions. And then imagine we transition to the squats mode and have 2 possible transitions, and so on. Well, in everything I've described so far, I've assumed that there are capital K different possible dynamic modes. Well, this begs the question, what if this isn't known ahead of time? And what if we'd like to allow for new dynamic behaviors to be incorporated into our model as we observe more data? Well, in such scenarios, an attractive approach is to appeal to Bayesian nonparametrics. So again, let's recall this example where you have data generated from some mixture of Gaussians with an unknown number of mixture components. Well, in this case, the Dirichlet process provides a useful prior by defining an infinite collection of mixture weights and associated parameters. And specifically, the weights, the construction of the weights can be described using what's called the stick breaking construction. So you start with a stick of unit probability mass, and then you draw a number from this beta 1 alpha distribution. So it's some number between 0 and 1, and you break off that portion of the stick, and you call that your first mixture component, your first mixture weight. Then you draw another number from this beta distribution, break off that portion of the remainder of the stick, call that your second mixture weight, and you keep repeating that process infinitely many times, hopefully not here, and this defines our countably infinite set of mixture weights. Then the generative process says that for each one of our observations, we're first going to select a mixture component from this infinite set of mixture weights, and then that observation is generated from the selected Gaussian component. Well, the Dirichlet process has a number of properties that make it quite useful in practice, and I'm not going to go into all of them in detail here, but the main thing to bear in mind is the fact that the Dirichlet process reinforces components of the model that we've already seen in the data, while still allowing for new components to be added as more data are observed. Okay, well, it's been shown that a hierarchical layering of Dirichlet processes provides a useful prior for HMMs with an unknown number of dynamic modes. So this is the case where we're letting k tend to infinity. And the way it does this is by defining these countably infinite transition distributions. So the Dirichlet process is what allows for this unbounded mode space, just like it allowed for an unknown number of mixture components in the standard mixture Gaussian case. And it's also the Dirichlet process that's going to encourage using a sparse subset of this infinite mode space. The hierarchical layering of Dirichlet processes is needed in order to couple the different transition distributions, because you want the set of modes that you can visit from some mode J to be somehow related to those that you can visit from some mode K. Okay, so this leads to a shared sparse set of possible modes visited. Okay, and so this model is referred to as the HDP HMM for hierarchical Dirichlet process hidden Markov model. And we developed a generalization of this HDP HMM in order to better capture the temporal mode persistence that we see in many real data sets. And we refer to this model as the sticky HDP HMM. So the way the model is described is we start with a global transition distribution, beta, that's a draw from a stick breaking construction. So the same procedure that I described earlier. And then we define a collection of mode-specific transition distributions that are each a draw from a Dirichlet process where the base measure has an additional weight on the component that corresponds to self-transition. So just qualitatively to get a picture of what's happening here, each of the mode-specific transition distributions is centered around beta, but there's this bias on the component that corresponds to self-transition. So here's pi 3 and pi 4. So in red, I'm highlighting this prior bias towards self-transitions. And so this is what's going to encourage this mode persistence. And so actually using this construction, you can show that the expected set of weights are a convex combination of the global weights defined by beta plus some mode-specific weight given by this kappa parameter, which we call the sticky parameter. So the sparsity that's induced by beta is then shared between each of these different modes. Okay, well, one of the important things is the fact that we actually don't set the prior bias for self-transitions ahead of time. Instead, we place a prior both on the HDP concentration parameters and also on the sticky parameter, and we try and learn the bias towards self-transitions from the data. And another thing to note is that if you set this kappa parameter to 0, you exactly return to the HDP HMM of Tay et al. So, yes.
Sorry, is there only one kappa?
There is only one kappa.
So setting the hyperprior is just kind of an indirect way of setting kappa. If there were a lot of kappas, setting the hyperprior would be something to...
Right.
So... Nice thing. In this case, it just seems like a way of pretending you're not actually setting it.
So, well, I mean, you still have, even though kappa is shared between each of the different modes, you still have prior uncertainty in the value. Like, is my prior bias towards self-transitions going to be centered around 0.4?
The hyperprior has its own parameter.
The hyperprior has its own set of parameters. Yeah. Yes. Yeah, and you could, of course, think of extensions where every HMM state has its own kappa parameter, and they're hierarchically coupled. And, of course, in the posterior, from state to state, the posterior probability of self-transition is going to be different. But yeah, it's a good point.
I mean, it might be that you have multiple tasks or something like that.
Exactly, and some of them have more. Exactly, yeah. So the applications I looked at, you didn't really need that, but of course there are some where you could trivially extend that to that case. So yeah. Okay. So just to get a little intuition about the difference between this original HDP HMM formulation and this sticky variant, it's useful to look at draws from the prior. And so on the left-hand side, I'm just looking at a draw of the mode sequence, so this underlying discrete valued label sequence, from this original HDP HMM. And here's a draw from our sticky variant, where first we're going to draw a sticky parameter from its prior distribution, and then draw the mode sequence condition on that sticky parameter. And so if these labels are going to represent things such as who is speaking when in conference audio, or which exercise routine or exercise type am I doing within an exercise routine, well, the dynamics I see here much better capture the type of dynamics I expect in a lot of these real-world applications as compared to this very rapid switching between different HMM modes. And so we're going to show that it's very important to capture this idea of temporal mode persistence in the prior. Okay, so one data set that we looked at is the task of speaker diarization, where you have some conference audio and you're trying to parse it into these speaker homogeneous regions in the presence of an unknown number of speakers. So specifically, we had data from the NIST speaker diarization database. So there are 21 recorded meetings with ground truth labels. We don't use the ground truth labels for any kind of training. They're just going to be used for assessing our performance. So this is a fully unsupervised approach that we're taking here. And so NIST runs this competition every year. And at least at the point of doing this project, this team out at Berkeley, the Berkeley ICSI team, had won this competition by a large which are the first 19 dimensions of non-frequency capsular coefficients. And one thing to note is that I mentioned this earlier in the meeting, these features were actually designed for speech recognition. They're supposed to be variant between speakers. So it's very challenging to actually try and discriminate between speakers using these features, but this was the task at hand, to have exactly the same feature set, so we're not tweaking the features.
And are MFCCs the only features that you have in the data, or do you
Yes.
have?
So yeah, we don't augment with deltas or anything. We constrained ourselves to having exactly the same setup as this other team in order to be able to have a fair comparison, just looking at the sticky HTTP HMM relative to cooperative clustering with the same data set.
So just to be clear about the setup, the Ys, the outputs here are the MFCCs,
Exactly.
and the states are the speakers.
Exactly,
Right?
that's exactly right.
Thanks.
And so we have these, per meeting, we have these 19-dimensional time series that we're trying to parse them. Okay.
So the part that's not being accounted for in using kappa is the question of who is likely to follow who.
Right. So this slide will maybe illustrate the importance of this, which is the fact that, so we just did some exploratory data analysis. We took one meeting where there were 4 different speakers, and we just looked at what their emissions looked like. And so here I'm just showing plots of the top 2 PCA components, a kernel density estimate of their emissions. And what you see is that typically when you're restricting yourself to HMMs, you're restricted to some parametric emission distribution like Gaussian, multinomial, or something of the sort. However, these speaker-specific emissions are clearly very multimodal, and if you're just to approximate each using a Gaussian, you would have a very hard time discriminating between speakers, right? Because they have significant overlap, and really the key differences are in the tails of these distributions. And so instead, what's typically done in this domain is each speaker is modeled as a mixture of Gaussians. Okay, but there's an issue when you're looking at an unbounded number of speakers, each modeled as a mixture of Gaussians. Do I create a new speaker with fewer mixture components, or keep the same speaker with more mixture components? So there's this question like, do I parse up my speech into multiple people, each with fewer mixture components, or just have me speaking? And so the key thing that allows us to disambiguate between these two situations is the fact that there's this Markov structure on the speaker label, right? And so we harness the fact that I speak for some period of time, then somebody else speaks for some period of time, and that allows us to identify this type of model. So what we're going to do is we're going to model each speaker as an infinite mixture of Gaussians. So we're allowing for an infinite number of possible speakers, and every speaker's emission is an infinite mixture of Gaussians. So we're doubly infinite. So we have to extend our HTTP HMM to account for this. And what we showed is that both the incorporation of the sticky parameter and these Dirichlet process mixture Gaussian emissions were very key in our performance. So here I'm showing the overall DER, which is speaker diarization error rate. It's a standard NIST metric. It's basically just a calculation of the percent of incorrect speaker labels. So lower is better. So here's the performance from the Berkeley ICSI team. And our sticky model with these mixture Gaussian emissions has comparable performance. It's slightly better, but let's just call it comparable in the same ballpark. But if you simply look at a non-sticky variant, so having the mixture Gaussian emissions, but running exactly the same thing with kappa equals 0, that's the only change. You have significantly worse performance because it has a lot of uncertainty between these rapid switching dynamics. So just to look at this in a bit more detail, we can look at meeting by meeting. So this was, the number I showed you before was overall averaged over the 21 different meetings. But if you look at our meeting by meeting DER, I'm comparing the sticky model to the non-sticky variant, where this red dashed line is a line of equal performance. So you can clearly see the dominance of the sticky variant over the non-sticky model. And here I'm comparing to Berkeley ICSI's performance. You can see our rather comparable performance. In this table, we also show the best and worst DER over the 21 different meetings. Okay, well, let's look at some of the results. Yeah.
You say that the training procedure is completely unsupervised, but if you do have one sort of parameter, which is the prior on the kappa, right, and that's something that you choose.
Right. And
It's
so
something you got to play with.
So actually, we did it. I mean, so ideally what you want to do in these Bayesian procedures is be able to tweak that hyperprior a bit and say that it didn't influence your results. Right? You don't want it highly tuned because you get a new meeting and it's probably going to do pretty poorly on this kind of out sample. And so we have a rather non-informative setting on that parameter.
So in that case, does it kind of reduce to empirical base almost?
Yeah, it is.
So the whole thing is that the kappa were really small, but not zero. Then your sticky pH and that would be sort of switching on the phone as opposed to the speed. Right? So it seems like it would be very sensitive in the sense that your prior on kappa is going to the effect, and your ultimate kappa
Right,
is going to
in
affect
terms of granularity.
Right.
Once you get out of the granularity sense, right? Yeah, so you need a, I mean, you're right that you could have it that it's persisting for one observation and then, you know, on that level. There are a couple other details that I don't get into where, and this is typical for speaker diarization, is you set a minimum duration. We didn't actually force a minimum duration, but you cluster certain observations under the same state label. So in that way, you're forcing it to not switch at the level.
So one thing that seemed to be interesting is that if you inserted an extra layer in there, somewhere between the speakers and the observation, that would handle some number of states per phonemes for each
Right.
speaker.
Yeah.
And then let the kappa switch within that frequently, but less frequently with the layer above the speaker, and you might ultimately uncover.
Right, so I mean, we did look at an extension to basically where, go back, instead of independent mixture components over time, that there's a Markov structure here, and in practice it actually didn't help us that much. I mean, it increased computational complexity, but yeah, I mean, there are a lot of variants that you could use to capture a lot more structure in this application domain. Of course, they often come at a cost in terms of these are big data sets. Okay, so I just want to show a couple qualitative results. And so here's one meeting where we did really well. Our DER was just above 1%. And so the errors, so on the left I'm showing the true speaker labels as a function of time, and on the right the estimated speaker labels, where the errors are shown in red. So very few errors, but pretty hard to see probably from where you are. But here's a meeting where we had very high DER, okay? Over 20%. And what you see is that our errors are attributed to taking one true speaker and splitting into multiple estimated speakers, or in this case, merging a speaker. So it's possible that the speaker looks different over time. Maybe I get tired, or I become angry, or something changes in my speech. So it might not be all that unreasonable to split a speaker. But one of the benefits of taking this Bayesian approach is that we have a posterior over different segmentations. We can provide multiple possible segmentations. This was our top segmentation. But if you look at one of our top 5 segmentations, it has significantly lower DER. And so that's one of the benefits here as opposed to the glomerative clustering approach, which provides one possible segmentation. Okay. Well, up to this point, we've described the Bayesian Nonparametric approach to hidden Markov modeling. And although a very flexible time series model, the HMM makes this very strong assumption that the observations are conditionally independent given the underlying dynamic mode. So in a lot of applications, this is really insufficient in capturing the dependencies present in the data. So just as an example, let's return to this honeybee dance. And so honeybees, they do a waggle dance, turn right, turn left dance within the beehive. And let's assume that the switches between these dances can be described as Markov. And let's just look at the turn right dance. Well, the observations within the turn right dance are clearly not independent. If you give me the honeybee's body position at one time step, that's highly predictive of the position at the next time step. Okay, so we're going to turn to looking at a class of models where there are conditionally linear dynamics for each one of our different HMM modes. So I'm just going to quickly review the 2 different linear dynamic models that we're going to use. One, so I mentioned these at the beginning of the talk, but let's just review one quickly here. So one is a linear state space model. So I mentioned the state evolves according to this linear dynamic matrix A, and is projected down to our observations. And both are corrupted by additive Gaussian noise. So if you look at the graphical model structure, it looks exactly like a hidden Markov model, except the key thing that to bear in mind is the fact that this underlying state process is continuous value. So that's in contrast to the discrete state space of a hidden Markov model. And so another linear dynamic model that we're going to look at is a vector autoregressive process. So a vector autoregressive process assumes that your vector of observations at time t are a linear combination of some r previous observations plus some additive Gaussian noise. And so you can write every var process in state space form by, for example, the following transformation. And so as such, the class of var processes are a subclass in those of state space models. Okay, well, let's return to these switching processes. And we're going to look at Markov switching processes where the switching mechanism is exactly as it was in the sticky HDP HMM. So this is our sticky HDP HMM. But instead of having these conditionally independent observations, in one case we're going to look at conditionally vector autoregressive processes. Okay, so the mode, the HMM mode evolves in this Markov fashion, and then conditioned on the mode, there's mode-specific vector autoregression. And we refer to this as the HDP AR HMM for autoregressive hidden Markov model. We're also going to look at a model where conditioned on the HMM mode, there's this conditionally linear state space formulation. And we refer to this as the HDP SLDS for switching linear dynamic system. Okay, and so again, based on what I showed on the previous slide, our class of switching autoregressive processes is a subclass of those of the switching state space models. And if you set the autoregressive parameters exactly to 0, you return to the case of Gaussian hidden Markov models. So we have the following nested classes of models that we could consider. Okay, well, I mentioned that the switching mechanism is exactly as it was in the sticky HDP HMM. So the only question now is, what's going to be our prior specification on the parameters associated with these different conditionally linear dynamic modes? So inherent in that question is a question of model order. So for the switching var process, that is, what is the autoregressive order R? statement in the land of state space models is what's the dimension of this latent state vector x. So again, we're going to assume that it might have some uncertainty in this. And we're going to assume a higher order model and then employ a sparsity inducing prior. So for the state space model, we're going to decompose our prior over the columns of this dynamic matrix A. And specifically, we're going to assume each column is normally distributed with gamma distributed precision. And what that's going to do is it's going to encourage shrinking entire columns towards zero, implying that that component of the state vector is not contributing to the dynamics of this mode. And then for the switching var process, we're going to look at decomposing our prior over entire lag matrices. Okay, so let's assume a maximal order of 2. So we looked at 2 lagged observations. Well, our prior specification encourages shrinking an entire lag matrix to 0, which means that this lagged observation does not contribute to the dynamics of this mode. So this allows us to look at variable order switching processes. Okay, so we applied this HDP SLDS to the problem of detecting changes in the volatility of the stock index. And in particular, we looked at the Evo Vespa stock index from January 1997 to January 2001. And our model is going to be a standard Markov switching stochastic volatility model. So we take our observations to be log squared daily returns so that the underlying state x has the interpretation in terms of log volatility. And so this is a standard model, but typically people assume either 2 or 3 regimes of volatility, high, medium, low, something of the sort, whereas our HDP SLDS is going to allow for an unbounded number of regimes of volatility. And so during this time period, there were 10 key world events that were cited as having affected this emerging Brazilian market during this period of time. These events were cited in this paper by Carvalho and Lopez. And I show them with the dashed red lines here. So just as an example, this event corresponds to the Hong Kong stock index falling by 10.4%. And so in blue, what I'm showing is the inferred posterior probability of a change point at each day during this series. And so you can see that our inferred change points align quite well with the true world events. And if you simply, again, set this sticky kappa parameter to 0, you get the following results. So you have a bunch of inferred change points that have nothing to do with the world events. So the fact that there's also, in the case of the switching linear dynamic system, this latent state process, that further obscures the dynamics from the underlying discrete switches between these dynamic modes. So it's very important in this case to be able to capture this idea of mode persistence. So you can also look at ROC curves, so looking at our detection performance, where we're going to declare a detection if there's an inferred change point within some small window around the true world event. And so we're comparing an order 1 and order 2 switching autoregressive process to our HDP SLDS, both with and without the sticky parameter. And from this, you see the importance of incorporating the sticky parameter and using this SLDS formulation. Okay, well, as a second demonstration, I want to return to this case of analyzing dances of honeybees. So, as I mentioned, honeybees switch between a set of dances in a beehive, a waggle dance, turn left dance, and you'll see a turn right dance as well. And so they do these dances in order to communicate the location of food sources to other bees in the hive. And so the setup here is that there's a camera that's monitoring this beehive, and then a computer vision tracker gives us tracks of these individual honeybees. So we're going to look at 3 different honeybee dances, and our computer vision tracker is going to give us estimates of the X and Y honeybee body position, as well as the head angle, which we decompose into sine and cosine. So we have these 4-dimensional time series, and we also have a set of ground truth labels, or the labels generated by a honeybee expert. somebody's job to study this. And so we're going to use these again, not for training, but just for assessing our performance. And on the top panel here, I'm showing the labels according to this honeybee expert. And I think, honestly, through this process, I became a honeybee expert myself. And there are times where I disagree with this other honeybee expert. But aside from that, we're going to use these as our labels. And on the bottom panel, I'm showing our estimated label sequence. I haven't gotten into any of these details, but we run this GIF sampler. We have many different samples of possible segmentations. And this one that I'm showing just represents our median performance. So it's not our best performance, just median error. And what you see is we've clearly been able to identify these 3 different dance regimes. But in addition, and you can see it here, there's these white stripes. And so you might wonder what those are. Well, it's a 4th inferred dance mode. And so if you look closely at the data from this honeybee dance, there's something weird going on during the waggle dance. For a while I said he was just a cat dancer, this honeybee, but it turns out, talking to the people who gave us this data, there's an issue with the computer vision tracker during this period of time. But anyway, the thing is that by not forcing ahead of time 3 different dynamic regimes, we're able to detect this type of anomalous behavior. So here on the bottom I'm showing accuracy of our labels, so higher is better. And I'm comparing by the people who gave us this data, San Reno and his colleagues down at Georgia Tech. And so they use an approach that I call super supervised. They fix the number of dynamic regimes to be 3, and then they use a lot of application-specific information from this data set, such as cues from the honeybee's head angle, in order to propose label sequences. But without using all that application-specific information, you see that we achieve pretty comparable performance. And so another thing I wanted to note, going back to this question of hyperparameter settings, we actually had exactly the same hyperparameter settings in this application as we did for stochastic volatility. So there was no tweaking, we just passed different data sets and it inferred these different underlying dynamics. So we did, however, in all honesty, we did a quasi-empirical Bayes procedure and we set our base measure, so not the hyperparameters, but our base measure from statistics of the data. So there is data getting thrown in here somewhere. Okay, so the last thing I wanted to mention on this application is the effects of our sparsity-inducing prior. Yeah.
So before we move on, could you at least comment a bit about all the learning procedure that's being done? Specifically, I'm assuming there's some sort of EM going on, or
so I'm running a GIF sampler, actually. And so there are a lot of ways you could do it in this. I can have a 2-hour talk on just how you do computations in these models. We end up considering a truncated approximation to the model, which allows us to run the forward-backward algorithm to have computations that are on the same order as just normal parametric hidden Markov model. But even if we fix k possible dynamic regimes, the priors still encourage it using a sparse subset. So there's specific structure to it, but if you're familiar with forward-backward algorithm and computations in these models, there's nice additional conjugacies that we harness to have a GIF sampler procedure.
I think your slide about the stock market example mentioned particle filtering as well.
So this other approach that the other paper took used particle filtering.
Yep.
So yeah, if you wanted to do online types of procedures, you could look at particle filtering extensions, but everything I was doing was looking at batches of data, and looking at sampling over the entire series.
So one thing that's confusing me a little bit right now is that you mentioned using a forward-backward algorithm, and I thought that you also said that you're changing your model over time so that half of work can infer that is data, am I right?
Yes, but
So
it's using.
okay. So I don't understand how you can do that, but I would think that for forward-backward algorithm you would need all the data from.
Right. So this is this point that I'm saying. I'm looking at a batch of data. I'm not doing an online inference procedure.
Okay.
I'm batch of data with uncertainty in the number of HMF states within this batch of data. So in theory, if I increase the batch of data, either I can rerun the procedure on the whole increase process, or I could look at other online techniques based on sequential Monte Carlo methods, or techniques such as that. Okay, so getting back to the effects of the sparsity-inducing prior, I compared an order 1, order 2, and order 7 switching vector autoregressive process with the conjugate prior, so it's not a sparsity-inducing prior, to an order 7 switching process with the sparsity-inducing prior that I described. And specifically, we're going to train on the first half of each one of these honeybee dance sequences and learn a set of parameters using the skip sampling procedure. And from this set of parameters, we're going to look at the predictive held-out likelihood on the second half of each of the dance sequences. And so in these plots, I'm showing the 95 highest posterior density intervals of this predictive held-out likelihood, or log likelihood. So here is our order 1, order 2, and order 7 model with a non-sparsity-inducing prior compared to our sparsity-inducing prior with order 7. And so what you see is this is kind of your classic overfitting curve where the likelihood's improving as you're increasing model order, but only to a certain point after which it starts overfitting. But providing this regularization through the sparsity-inducing prior helps us ameliorate this issue of overfitting. And so another thing that the sparsity-inducing prior allows us to infer is this variable order structure. So I don't have plots of this here, but what we found on the honeybee dances is that the inferred turn right and turn left dances were very well approximated using an order 1 autoregressive process. But the waggle dance relied very heavily on the second order lag component. So it's interesting to be able to look at that kind of structure. Okay, so finally I want to get to this problem of relating multiple time series. So remember that we had a collection of videos of people performing some set of exercise routines, and we wanted to somehow jointly model them. Well, if we applied the types of time series models I've described so far independently to each of these time series, they would necessarily define completely disjoint state spaces. We'd have to rely on post hoc procedures to identify which behaviors were the same. Instead, a naive approach to jointly modeling the time series is to assume that they share exactly the same underlying state space. However, what we'd really like to capture is that there's some sharing of dynamic behaviors, but also some variability. So perhaps in one movie, a person does side twists, but that motion doesn't appear in any of the other movies. Okay, so we're going to start by modeling each one of our time series using a switching vector autoregressive process. And then, in order to jointly model them, we want to somehow couple them under a common prior. And again, in order to allow for uncertainty in the number of dynamic behaviors, we're going to appeal to Bayesian nonparametrics. So one possible approach is to couple all of these time series under a common HTP prior, just like the models described earlier. So this model allows for an unbounded state space, which is great. However, it assumes that each of the time series are switching between exactly the same behaviors in exactly the same fashion. So this is clearly not as flexible as the model we wanted. This is the case of identically shared state spaces. So instead, I'm going to describe how an alternative approach based on the beta process allows us to start addressing these goals. So just as a quick background on the beta process, a draw from a beta process can be described as a collection of weights and atoms that are a draw from a non-homogeneous Poisson process. So each of the weights is constrained to be between 0 and 1. So you can think of it as defining a coin flipping probability. And through this construction, we're defining an infinite collection of these coin weights. So I show one realization here. And then one can use this beta process measure to define observations from the Bernoulli process, which are collections of unit mass atoms that are the results of coin flips at each location of this beta process measure. So specifically, we walk along and we flip a coin where the probability of getting a heads is given by the weight of that atom. So here we got a heads, another heads, tails, and so on. Well, because this beta process measure has finite expected mass, we're going to get a finite number of successes in this infinite coin flipping sequence. And we can think of this infinite coin flipping sequence as defining a feature vector, or an infinite dimensional feature vector, where the set of selected features are the locations in which we got a heads. Okay, well here I show a collection of observations from this Bernoulli process, each based on this underlying beta process random measure. So by sharing the same base measure, you see a lot of sharing of features, but also some variability. And what makes this process so useful in practice is the fact that one can actually analytically marginalize this underlying random measure and look at the predictive distribution on a new feature vector based on the observations that we've had so far. And so this process is commonly referred to as the Indian buffet process. So just as the Dirichlet process yields the famed Chinese restaurant process analogy of partitioning observations into clusters, the Indian buffet process is the description based on the beta Bernoulli process of taking observations and assigning them to features. So specifically, imagine you have a buffet line with infinitely many dishes, and customers arrive at this buffet and select some set of dishes. So the first customer arrives and chooses some Poisson set of dishes. Well, the next customer arrives, is more likely to sample the dishes that the first customer chose, then gets the end of the set of sampled dishes and chooses some Poisson set of new dishes himself. And this process continues where every customer samples dishes in proportion to how many people have sampled them so far, and then samples some set of new dishes. So here I show a feature matrix associated with the draw from this Indian buffet process, where every row corresponds to a different customer, and every column is a different dish, and the white squares indicate the set of selected dishes. You might be wondering what any of these feature models have to do with relating multiple time series. Just recall that each one of our n individual time series we're modeling with this switching autoregressive process. Well, this feature matrix, which in general corresponds to some set of customers eating some collection of dishes, is now going to correspond to each one of our time series selecting some subset of dynamic behaviors. So specifically, we start with this shared library of infinitely many possible dynamic behaviors, like jumping jacks, squats, and so on. And then each time series is endowed with an infinite dimensional feature vector that indicates which of this infinite collection of dynamic behaviors this time series is going to switch between. And the way it does that is by operating on a collection of transition distributions. So specifically, imagine that you define some set of transition distributions in an infinite dimensional space, and then you do an element-wise product and renormalize based on the time series feature vector. And this defines what we call our feature-constrained transition distributions, because it constrains this time series to only switch between the set of selected behaviors. Okay. Well, the generative process then says that each one of our transition distributions is Dirichlet distributed only along the components specified by the given feature vector. And again, this kappa parameter is just like the sticky parameter before, that's going to encourage self-transitions. Then, based on these feature-constrained transition distributions, the mode evolves according to this Markov structure, just as before, and then the chosen dynamic mode indexes into the shared library of infinitely many possible behaviors to select the one that's driving the vector autoregressive dynamics at that time step. Well, we're going to couple all of the feature vectors under a common beta process prior, which encourages sharing of dynamic behaviors between the time series while still allowing for some variability. So I really haven't gotten into how we do computations at all in these models, but I just wanted to allude to how efficient things are in this case. One thing that we harness is the fact that conditioned on a feature matrix, our model decomposes into a collection of finite switching far processes, and we know how to do inference for those. Specifically, even though there's an exponentially large number of possible latent state sequences, we can analytically compute the likelihood using the forward and backward algorithm, and then we can weight this likelihood by this Indian buffet prior. So we run our MCMC sampler in this using this type of procedure. Okay, let me get to some results. So we analyzed a collection of 6 different videos taken from the CMU mocap database. So they dress up their grad students in these mocap suits, and it provides measurements of 62 dimensions of body position and joint angle measurements. So we run our sampler, many iterations, and we're going to look at the segmentation that minimizes an expected loss criterion, and with the goal of discovering common behaviors between these 6 videos. And so here are the results from that segmentation. So each one of these skeleton plots corresponds to learn a contiguous segment of at least 2 seconds of motion. And we're grouping together all of the skeleton plots that are labeled as having been generated from the same underlying dynamic behavior. And the color of the box indicates the true behavior category. So from this, you see that we've been able to identify these 6 examples of jumping jacks that appeared in these different movies, as well as side twists, arm circles, and squats. And one nice thing about our formulation is the fact that we've been able to identify a set of dynamic behaviors that appeared in one and only one movie. We did, however, split a couple motion categories. For example, knee raises. But if you look closely at the data, there's a reason for this. In one case, this case here, the person has a lot of side-to-side upper body motion as they're going through their knee raises, whereas the other person does the more standard motion. And same for the running motion. In one case, I practice this a lot. I don't know how the person does it, but they're running with their hands in place with their knees. And the other person, the more natural running motion. And this person is in the middle of doing a jumping jack as they're running, so just generally confused. But that's what happens when you ask computer science grad students to do some exercise with this. As a computer science, it's okay. But overall, you see that we've been able to identify these different dynamic behaviors that appeared in a collection of videos, while still encouraging the sharing, while still allowing for this variability. So one other way to look at this is by looking at the inferred feature matrices. So here is the true feature matrix. Remember, each row is a different video. Each column is a different behavior, like jumping jacks. And here's our inferred feature matrix, averaging over a large collection of MCMC samples. This is for our beta process-based model. And we also compared to a couple other algorithms that were proposed in the literature, a Gaussian mixture model and a hidden Markov model, both on first difference observations. These are parametric models, so we fixed the number of dynamic regimes to 12, which is the truth. We learned them using EM, many initializations, choose the most likely, so we're trying to be as nice as possible. But by pulling together all the data, you see these strong bands of white. And finally, here's a model that couples each of the time series under a common HTTP prior. So this was the first model I proposed as an option. And what you see is that by taking this feature-based approach, we're able to uncover this unique feature structure without adding all these extra dynamic regimes. Okay, yeah.
So do you have a sense of how this would work if the input were the actual video as opposed to the schematic?
So in everything I'm doing, I'm assuming you have some representation of the time series. So if there's some intermediate stage of taking the video and parsing it into some feature-based representation of motion, it could do reasonably well. But in terms of just, there is an assumption that you have some representation that should somehow be informative of.
Yeah, I think, the difference between the kinematic parameters of the motions versus the image is some presumably complicated dynamic transform that would become the burden of the training procedure if it weren't already done.
Right, but I mean the description for sure that the there's some other nonlinear transformation that's present in that, but even description of a jumping jack is rather complicated dynamic, right? And so, again, I mean, there are always ways in which you can augment the model to incorporate more complex structure. I mean, really what I want to do is infer some lower dimensional embeddings of these dynamics or some enough that my dynamics are constrained to based on the geometry of my body. And so it depends what's the task at hand. Am I trying to predict human motion, or am I trying to segment? And you can define arbitrarily complex models, but it's always, I think, motivated by what task you're trying to solve. So I guess when you say given video, I mean, I would obviously need to analyze that video and explore it, but yeah, you can always consider extensions to it. The models are assuming an underlying conditionally linear dynamic, but the question is, if you're trying to do predictions, maybe I don't care if I parse up my jumping jack into 5 different modes that are conditionally linear if I'm trying to predict the next observation. Maybe that's okay. If I actually want to do segmentation, somehow I need to hierarchically group those, but it's always a question of what's the task at hand. Okay. But in this talk, we've examined a set of Bayesian nonparametric models that extend the classical hidden Markov model, switching autoregressive process, and switching linear dynamic system. And we also looked at this feature-based approach to relating multiple time series. We chose this Bayesian nonparametric approach based on the beta process, but the same idea of feature-based approach could be used within parametric modeling as well. And we demonstrated the performance on a number of different data sets, including this problem with speaker diarization, detecting changes in the volatility of the stock index, and analyzing this motion capture data set. First, can I ask a question?
We're just about out of time, but I think we can get in one more question.
Oh boy. So,
If you could.
think of the speaker diarization thing. And I want to know how persistent the model of an individual talker would be as compared to how it just depends on the other talkers who are at that conference. In other words,
Are there some who are much less consistent?
well, suppose you have another conference
Right.
and some of the talkers repeat and some of them are new. Would you get similar models for the repeating talkers from session to session, or is it highly dependent on knowing who the other, having other talkers and drawing boundaries between them?
Okay, let me make sure I understand. So,
So-
is your
so
question
could
in
you
terms
build-
of the duration of modeling the duration per speaker, or everything associated with that speaker?
Everything with the speaker. In other
Okay.
words, could
So-
I end up with a model of that speaker that I could just apply generically?
So, in terms of, I found that looking over a large collection of these meetings, that in terms of the duration distributions, they're surprisingly similar. So this idea of the shared kappa and having this one prior model on durations was okay. But in terms of the emissions, if you want to separate between men and women, I'd say yes. That you could come up with some model. So I'm make sure Gaussian emissions for men.
Yeah, I think Tom's question is different. No, Tom's question is different. This question, I think, is if you simultaneously diarized all 21 NIST
Right,
meetings,
okay.
would you be able to identify a speaker appearing in multiple
I understand.
meetings?
Okay. So, okay, that I understand. So, I mean, my hunch is yes. I mean, this prior is trying to encourage as few speakers as possible. So, if anything, honestly, in these meetings, it would take, you can look at trace plots of this, but they have speakers merged, and it takes a while until it kind of, the sampling gets to the point where it splits them. Because the speakers, like I said, based on these features, aren't that distinguishable. And so, it was actually more this issue of how do I pick up on these very subtle differences between speakers than how do I merge speakers. So, I would imagine, without trying this, that if you put 2 meetings or all of them together and you had the same speaker appearing, then you would group them. Assuming the same kind of recording conditions and all that.
about, have you tried to figure out how much the Bayesian stuff buys you? If I did something more straightforward, like an MDL or something where I just sweep a number of parameters, look at some mean, the likelihood curve, wouldn't I get the same thing?
In terms of the segmentation performance?
Or whatever you care about.
So I would say not in whatever you care about. Yes, in terms of segmentation performance, there are many things that can segment things very well.
Okay.
So if you
Then what
care
are you-
about,
But you're only measuring segmentation performance, I thought.
so that was for the NIST example. I mean, so you're right, in this talk I presented things in terms of, so for the NIST competition, they care about segmentation performance.
No,
But-
even for the mocap data from CU.
Right. So yes, but I mean, I didn't put this in here, but in terms of the stock data, that's not true. You care about predictions, you don't care about segmentation. So I did, for many reasons, present everything here in terms of segmentation, but I'm a time series person, and the majority of what I care about is predictions. And being able to do the Bayesian model average thing, and averaging over my uncertainty to perform predictions, time and time again, you can show outperforms a number of other procedures. But I would say that in terms of coming up with a point estimate, that the Bayesian Nonparametric methodology is heavy-handed and ends up providing performance that typically can be the same as other procedures. But I will say at the same time that it tends to be fairly robust to different setups. So I didn't have to redesign what I did for the different data sets I looked at. Right, and so I'm not saying that there aren't other procedures that could have that property. I mean, like the collaborative clustering approach that they took, I mean, it had performance that was on the same order as our performance. But if you did want uncertainty over segmentation score to look at predictions, it would be useful.
You may be selling yourself short when you say that a point estimate is just as good. I mean, the advantage that you can get is you can take loss into account, and instead of picking the math estimate, pick something that will end up making your downstream application happy.
So, yeah, I mean, there
I mean,
have been a
having
number
a
of
cluster is
papers
helpful.
recently that have shown that the map estimate is really a bad thing to look at
Yep.
in these situations.
And it's particularly true with settings like this, where there might be lots of ways to explain the behavior.
Exactly.
And so things get split to different granularity.
Yeah, so there are other ways that absolutely that you could use the Bayesian framework to inform better types of point estimates, but yeah, I think often, in my opinion, it comes down to, are you harnessing the underlying uncertainty that's present in an application or not?
Because my intuition simply says if your hyper parameters aren't making a big difference, it's very likely that all the burden of modeling is in the lower levels, and you could get that from something like NPL.
So the fact that there's insensitivity to the hyperparameter settings at a higher level doesn't mean that the prior is useless.
No, I'm not saying it's useless. What I'm saying is that, after all, MDL doesn't ignore a prior. MDL simply has a naive or a simplistic way of,
Yeah, I mean, the other side of things that people will often argue, and I don't understand here to do it, is the theory associated behind it, right? People analyze a lot in terms of MDL compared to these other procedures, and that gets into a much more philosophical argument that I won't present here, but if you're going to start with the Bayesian framework, there's very nice theory for the properties induced by these processes. And thinking of underlying stochastic processes is very useful in thinking of extensions to other models. So in the end, I truncated the model. Right? I said I worked within this parametric framework, but that form of the truncated model had never been proposed in the literature. The only way I think that you would think of that specific form that has all these nice properties is to think of these underlying random measures. And when you think in terms of these measure spaces, these infinite random measures, it motivates a lot of nice extensions even within parametric modeling. So. Any questions?
Yeah, so you talked a lot about these other models and trying to incorporate like previous observations, I guess. Have you looked into like CRFs, and do you have any sort of insight into how using other observations in that sort of model would perform compared to your in-market model approaches?
It's an interesting question. I haven't looked into it, so I don't have a good answer about what you would end up with.
Right. Because
but
you don't really care so much about the generative advantage of the in-market models, right? Because you're not.
I mean, again, it depends. Like, are you interested in incorporating other features of the model later? And that's always nice to do within the generative framework. But I mean, in some of these applications, yeah, I would say that you don't need to be tied to the generative framework.
So it's just something you decided at some point I'm going to stay in this direction.
I mean, well, that's a very short answer to a lot of. I mean, again, well, okay, that's a short answer. I won't keep that.
So if we think about what you're doing as hierarchical modeling, you mentioned in an answer to Aaron that you have two levels of hierarchy in time structure. So you have, John tends to be followed by Sue in the meeting, and then within John, this state tends to be followed by that, or this Gaussian component tends to be followed by that Gaussian component. Right. So have you thought about deeper hierarchies or hierarchies where the structure of the hierarchies at variable depth? So some of us are working on probabilistic CFGs. So at that point you start thinking about calling action subroutines, which could get reused across a number of different settings. And you might, a PCFG is usually you have a bounded width, but you could also say that you've got this non-terminal, and it generates a sequence of non-terminal children according to a Markov process.
Right. No, I mean, I think those are really interesting extensions to these types of ideas that I've read about but haven't played with in this regard. So again,
Well,
short
we get to
answer
talk about
rather than we can talk more about it.